Right now, in laboratories across the planet, particles are doing things that should be impossible. They appear in two places at once. They communicate faster than light. They change behavior the instant someone looks at them. And the deeper physicists dig, the worse it gets. Some of the smartest minds alive now openly admit it. Reality may not be what we think it is. The universe may be a hologram. Time may not exist. Your future choices may shape the past. Stay with us. Like and subscribe if this hooks you. Because what comes next gets stranger fast. A cat that is alive and dead. A wormhole stitched from thought. A theory that says you are made of math. The walls of reality are cracking. Let's step through. A single particle is fired at a wall with two slits. It passes through both at the same time. Then someone watches, and it stops. This is the experiment that broke physics. For 2 centuries, scientists believed light was a wave. Then they believed it was a particle. The double-slit experiment forced them to accept something worse. It is both, and it decides which one to be based on whether anyone is looking. Here is what actually happens. Researchers set up a barrier with 2 narrow openings. Behind it, they place a screen that records where particles land. They fire electrons at the barrier, one at a time, with long pauses between each one. Each electron is a single piece of matter. There is no crowd. There is no wave to interfere with anything, but the pattern that builds up on the screen is a wave pattern. Bright bands, dark bands, the signature of ripples crossing each other. A single electron, fired alone, somehow interferes with itself. The only way this works is if each electron travels through both slits at once. It exists as a smeared possibility, a cloud of every path it could take. The screen records where this cloud finally settles. Then comes the part that broke everyone. Physicists wanted to catch the electron in the act. They placed a tiny detector at one of the slits. Just a small instrument to record which slit each particle used. Nothing else changed. The same setup. The same electrons. The same screen. The wave pattern vanished. The electrons started behaving like ordinary bullets. They went through one slit or the other. They piled up in 2 simple stripes. The interference pattern was gone the moment someone tried to watch. This is the observer problem, and it has never been explained. The act of measurement somehow changes what the particle is allowed to do. Looking is not passive. Looking forces the universe to choose. Without observation, the electron lives as a fog of possibilities. Under observation, it collapses into a single fact. A real version of this experiment was done in 2019 at the University of Glasgow, where physicists captured an image of quantum entanglement for the first time. Variations of the double slit have been run with photons, electrons, atoms, and even molecules made of more than 2,000 atoms. Every time, the same impossible result. This is not a trick of the equipment. This is how matter behaves at the smaller scales. Reality at its base layer seems to require a witness. Think about what that means. The chair you are sitting on, the screen you are watching, every atom inside your body, all of it is built from particles that, when alone in the dark, do not seem to have a definite location. They exist as probabilities. They become real only when something interacts with them. Albert Einstein hated this. He spent the rest of his life trying to prove it wrong. He failed. Every experiment confirmed it. The double slit was only the first crack in the wall. It told us that observation matters. It told us that particles do strange things when no one is looking. But the next experiment took it further. It showed that two particles, separated by miles, somehow share the same fate. Touch one, and the other reacts instantly. Even Einstein could not believe it. He called it spooky. He was right to be afraid. Two particles are created together, then carried to opposite sides of a room, or a country, or the galaxy. Measure one, and the other reacts in the same instant. No signal travels between them, no time passes. They simply know. Einstein called this spooky action at a distance. He believed it could not be true. He was wrong. Entanglement starts in a strange place. When two particles are made from the same event, they share a single quantum state. They are linked at the level of their core properties: spin, polarization, momentum. They become two pieces of one mathematical object. Now separate them. Carry one across the lab. Carry the other to another building. Then measure the first. The instant you measure it, the second one snaps into a matching state. If yours spins up, the other spins down. Every time, with perfect coordination. The distance does not matter. Experiments have done this with particles 800 miles apart, sent from a Chinese satellite called Mikyus, beamed down to two ground stations on Earth. The result still holds. The link is not weakened. The reaction is not delayed. Whatever connects entangled particles, it travels faster than light, or it does not travel at all. Both options break what physics is supposed to allow. Einstein refused to accept it. In 1935, he published a paper with two colleagues, Podolsky and Rosen, arguing that quantum mechanics had to be incomplete. There must be hidden variables, some secret information carried by each particle, set at the moment of their birth, that decided in advance how they would behave. It was a reasonable idea. It was also wrong. In 1964, an Irish physicist named John Bell wrote down a math test that could finally settle it. If hidden variables existed, the correlations between entangled particles could only reach a certain limit. If quantum mechanics was right, those correlations would go higher. For decades, the test was too hard to run. Then, slowly, the technology caught up. By 2015, 3 independent labs in the Netherlands, Austria, and the United States ran loophole-free versions of Bell's test. Quantum mechanics won. Hidden variables lost. The universe really does work this way. In 2022, 3 physicists shared the Nobel Prize for proving entanglement is real, beyond any doubt. The world above us, the world we walk through, sits on a foundation of impossible coordination. Here is what makes it haunting. Entanglement does not let us send messages faster than light. The information itself is random. You cannot use it to call someone on Mars. The connection is real, but it is sealed off from anything we would call communication. Yet, it is there, threading through every interaction, every chemical bond, every photon that bounces off your skin. The deeper question is what is actually being shared. The particles do not seem to be sending anything. They behave as if they were never separate to begin with, as if distance in some quiet way is an illusion the universe enforces on us but ignores in itself. Then physicists pushed further. They asked what happens if you not only watch the particles, but choose how to watch them after they have already finished their journey. The result rewrote what we thought we knew about cause and effect. It suggested that the present can reach backward and change the past. A photon leaves its source, it travels through the apparatus, it hits the detector. Only then does the experimenter decide how to measure it. And the photon, somehow, behaves as if it had known the answer from the start. This is the delayed choice experiment. It was proposed by physicist John Wheeler in 1978. It was performed for real in 2007 by a team in Paris, and it broke time. Here is the setup. Take the double slit experiment. Add one new feature. Decide whether to look at which slit the photon went through after it has already passed the slits. Make the choice at the last possible moment, when the photon is already deep inside the apparatus and only nanoseconds from hitting the screen. If you decide to watch, the photon behaves like a particle. It went through one slit. It has a clear history. If you decide not to watch, the photon behaves like a wave. It went through both slits. Its history is blurred. But here is the part that should be impossible. The photon already passed the slits before you made your choice. Its behavior at the slits should be locked in. It should not be able to change what it did in the past based on what you decide in the future. And yet, the experiment shows that it can. Wheeler took it further with a thought experiment using a distant galaxy. Light from a quasar, billions of years old, can be bent around a massive object on its way to Earth. This is called gravitational lensing. The light reaches us by two possible paths. Wheeler asked, what if we set up the experiment now, today, to either measure which path that ancient light took, or let it interfere as a wave? The light has been traveling for billions of years. The decision is being made on Earth, in the present. According to quantum mechanics, the choice we make today determines what the light did billions of years ago. This is not metaphor. This is the prediction. And the small-scale lab versions of it match the prediction exactly. The experiment was refined and repeated by a group at the Australian National University in 2015. They used single helium atoms and confirmed the result with no loopholes. The atom's behavior in the past depended on a decision made after the fact. Physicists are careful about how they describe this. The standard interpretation says that quantum events do not have a single definite history until they are measured. The past, in the quantum sense, is not a fixed record. It is a range of possibilities that becomes specific only when we ask the right question. But the language of cause and effect, the language we use to think about reality, does not survive this cleanly. Something we do now seems to reach back and select what happened earlier. Most of us picture time as a straight line. Past, present, future. The past is set. The future is open. The present is where decisions get made. Quantum mechanics does not respect that line. It treats the past as something fluid until it is locked in by observation. It treats reality as a story that is still being written, with the ending sometimes choosing the beginning. This raises a sharper question. If observation is what fixes a particle's history, what counts as observation? Is it a human looking? Is it a detector clicking? Is it any interaction at all? The answer, when physicists tried to find it, made the problem worse. It led directly to the deepest unsolved puzzle in modern physics. Before measurement, a particle is a wave of probabilities, spread across every place it could possibly be. After measurement, It is a single point, one location, one outcome, one reality. The transition between these two states has never been explained. This is called the measurement problem. It is the heart of quantum mechanics, and no one knows what is actually happening. The wave function is the mathematical object that describes a quantum particle. It is not a physical wave you could touch. It is a wave of probability. It tells you the chance of finding the particle in any given location if you were to look. The math of the wave function is precise. It evolves smoothly over time according to a clean equation written down by Erwin Schrödinger in 1925. As long as no one measures the particle, the wave function spreads, oscillates, and behaves predictably. Then, someone measures it, and the wave function does something the equation cannot describe. It collapses, instantly, across all of space. Every possibility except one disappears, and the particle becomes a definite thing in a definite place. The Schrödinger equation does not predict this collapse. It does not even allow for it. The collapse is added by hand, as an extra rule, because that is what we observe happening. This is the dirty secret of quantum mechanics. Half the theory is beautiful and exact. The other half is a patch. We use it because it works, but we do not know why it works or what it means. What is a measurement, exactly? The standard textbooks say it happens when a quantum system interacts with a classical measuring device. But every measuring device is itself made of quantum particles. Every detector is a pile of atoms. Where does the line between quantum and classical actually sit? This is called the Heisenberg cut, named after Werner Heisenberg, who admitted the line had to be drawn somewhere but never said where. Some physicists believe the collapse is triggered by sheer size. Once enough particles are involved, the wave function decoheres, and the quantum behavior fades into ordinary classical reality. There is real evidence for this. Decoherence has been measured in the lab. Larger objects do lose their quantum strangeness faster, but decoherence does not finish the job. It explains why we see a single outcome rather than a blur. It does not explain how that one outcome gets chosen. The math still allows every possibility. Reality somehow picks one. Other physicists believe the collapse is caused by gravity. Roger Penrose, the Nobel laureate, proposed in the 1990s that once a quantum system becomes massive enough to bend space-time in measurable ways, the wave function is forced to choose. Experiments to test this idea are now running in deep underground labs, using suspended mirrors cooled to almost absolute zero. Then there are physicists who believe the collapse never happens at all, that every possibility continues to exist in a different version of reality, and we only see one of them because we are inside it. That idea will return soon. For now, hold the strangeness. Right now, as you read this, every electron in your body is described by a wave function. None of those electrons have a definite position until something interacts with them. They are clouds of probability, briefly snapping into points whenever they touch the world. You are made of those snapshots, trillions of them, every second. What forces the snapshots to happen, what selects which one becomes real, is a question we cannot answer. And the next experiment scaled the question up. Past atoms, past molecules. It scaled it up to a cat. A cat is sealed in a box with a vial of poison. A single radioactive atom decides whether the vial breaks. Until someone opens the box, the atom is both decayed and not decayed. And so, according to the math, the cat is both alive and dead. Erwin Schrödinger came up with this in 1935. He was not trying to amaze anyone. He was trying to show how absurd quantum mechanics had become. He thought the example would embarrass his colleagues. Instead, it became real. The thought experiment was meant to scale the strangest up. If a particle can exist in two states at once, and the cat's life depends on the particle, then the cat must also exist in two states at once, a living and dead cat at the same time. This is called a superposition, and it sounds ridiculous when applied to something as ordinary as an animal. For decades, physicists assumed there must be a hidden line somewhere. Particles could be in superposition. Cats could not. The quantum world ended at some scale, and the ordinary world took over. Then experiments started to push that line. In 1999, a team at the University of Vienna put a buckyball, a molecule made of 60 carbon atoms, into a superposition. Each one of those molecules went through two slits at once. They were the largest objects ever to behave in a quantum way. Then the line moved again. By 2019, the same group put molecules made of more than 2,000 atoms into superposition. Real chunks of organic matter, large enough to almost be visible under a powerful microscope, behaving like ghosts, existing in multiple states, interfering with themselves. In 2021, physicists at the Delft University of Technology entangled a tiny drum, an aluminum membrane large enough to be seen by the naked eye, with another drum across the lab. Two physical objects, big enough to touch, sharing a single quantum state. The line keeps moving. Every year, larger objects show quantum behavior. No upper limit has ever been found. This is the unsettling part. If there is no limit in principle, then the cat thought experiment was not a joke. It was a real description. The only reason cats do not appear to be in superposition is that they interact with so many particles so quickly that any quantum strangeness collapses almost instantly. The superposition is destroyed before it can do anything visible. But destroyed by what? By the air molecules touching its fur. By the photons bouncing off it. By the heat of its own body. The quantum world is not separate from ours. It is the foundation of ours. Everything large is made of quantum things. The reason we do not see superposition in daily life is that the world is too messy and warm to preserve it. Inside isolated, ultra-cold laboratories, the strangeness comes back. Macroscopic objects start to behave like particles. Visible drums hum in two states. The boundary between the quantum and the classical begins to look less like a wall and more like a fog. This raises a question that haunts physics. If there is no real boundary, then reality at all levels is built from superposition. The solid world we see is just the part where the fog has cleared. Schrödinger's cat was meant to be a problem. It became a description. And the more closely physicists watch these systems, the stranger the next discovery became. It turned out that simply observing a quantum system over and over could stop time itself. A radioactive atom is about to decay. It has a clock ticking inside it, governed by quantum probability. Look at it once and nothing changes. Look at it constantly, and it never decays at all. This is the quantum Zeno effect. named after the ancient Greek philosopher who argued that an arrow in flight is, at every moment, frozen in place. Physics turned the argument into a real result. The idea is simple, and it is testable. In quantum mechanics, every measurement collapses the wave function. The system, after measurement, has to start evolving from scratch. If you measure it again before it has had time to change, you collapse it back to its original state. Over and over. Each measurement resets the clock. If the clock never gets to run, the system never moves on. This was first verified experimentally in 1990 when a team at the National Institute of Standards and Technology in Colorado used beryllium ions trapped by lasers. They watched the ions transition between two energy states. When they watched continuously with rapid laser pulses, the transition slowed dramatically. With enough watching, it stopped. The atom, simply by being observed, was held in place. This is not a trick of the equipment. The ions are not being shaken into stillness. They are being cornered by the act of measurement. Each look prevents them from doing anything else. The opposite version is also real. If you watch a system with the right rhythm, you can speed up its evolution, pushing it from one state to another faster than it would naturally go. This is called the quantum anti-Zeno effect. It has been observed in several labs since the early 2000s. Both effects share the same root. Measurement is not a passive recording. It is an active interference. The act of looking changes what the system can do next. Now think about what this implies. There is no neutral observer in physics. Every observation shapes the outcome. The universe does not have a setting where we can simply watch without interacting. Watching is interacting. There is a real-world consequence to this. Scientists are now exploring whether the quantum Zeno effect can be used to protect quantum computers from errors. The fragile quantum bits inside these machines tend to lose their state quickly. By measuring them in just the right way, researchers may be able to lock them into useful configurations longer. The Zeno effect is also studied in biological systems. Some researchers suspect that certain molecules in living cells might use quantum stabilization to perform tasks that would otherwise be impossible. The evidence is early and contested. The implications, if confirmed, would be enormous. But the philosophical sting goes deeper. The Zeno effect closes a strange loop. Observation does not just collapse a wave function. Observation, repeated, can pin reality down. Repeated enough, it can prevent reality from changing at all. This means time, at the quantum level, depends on attention. A particle left alone evolves freely. A particle stared at, frozen. The arrow of time, the relentless forward push of events, is not a fixed feature of the universe. It can be slowed, accelerated, even paused by changing how often we ask the universe what it is doing. And this is where the deepest crack appeared. If observation can freeze a particle, what counts as an observer? Does the universe need consciousness to do this? Does a measuring device count? Does a passing photon count? The answer, when it came, ended 100 years of comfortable assumptions. The universe, it turned out, does not allow local realism. At all. Two assumptions have guided physics since the time of Newton. Things have properties whether or not anyone measures them. And no influence travels faster than light. Together, these are called local realism. In 1964, an Irish physicist proved that both cannot be true. His name was John Bell. He worked at CERN. He spent his evenings on a side problem that most physicists had given up on. The question was whether quantum mechanics could be patched. Whether the strange behavior of entangled particles could be explained by hidden variables, secret instructions carried by each particle, set in advance. Einstein had hoped this was possible. If the variables existed, then quantum mechanics was just incomplete. The world could still be local, real, sensible. Bell wrote down a math test to find out. His theorem showed that any local realist theory had to obey a specific limit on how correlated two distant measurements could be. He turned the philosophy into an inequality, a number, a line in the sand. If experiments stayed below the line, hidden variables were possible. Reality could still be normal. If experiments crossed the line, no local realist theory could survive. For years, the test was too hard to perform. The equipment was not sensitive enough. The particles were too hard to control. Then, slowly, the experiment started. In 1972, Stuart Friedman and John Clauser ran a version of the test at the University of California, Berkeley. The line was crossed. In 1982, Alain Aspect in France ran a tighter version with faster switching. The line was crossed. Through the 1990s and 2000s, every experimental loophole was closed one by one. The detectors got faster. The distances grew larger. The settings were chosen by random number generators, even by light from distant quasars, to rule out any hidden coordination. Every test agreed. The line was crossed. Always. In 2015, 3 independent groups in the Netherlands, Austria, and the United States ran loophole-free Bell tests. The result was unambiguous. Local realism is wrong. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics for the experiments that proved it. Here is what the death of local realism actually means. One of two things must be false about the universe. Either particles do not have definite properties before they are measured, meaning reality is not real in the way we thought, or influences can travel faster than light, meaning space itself does not work the way we thought. There is no third option. Bell's theorem closes that door. Most physicists choose to abandon realism. They accept the particles do not carry hidden answers. The properties we measure are not revealed. They are made, brought into being by the act of measurement. But this is not a comforting choice. It means the world we walk through is, at its base, undecided until something forces it to commit. The chair beneath you has a definite shape because trillions of interactions are forcing it to. Atoms collide, photons bounce, the wave functions of every particle are constantly being collapsed by their neighbors. The classical world is the result of an ongoing storm of measurements, with the universe constantly asking itself what it is. If that storm stopped, the chair would not. Bell's theorem is sometimes called the most profound discovery in science. It tells us that the deep machinery of reality breaks at least one of our oldest assumptions. The world we thought we lived in does not exist. And one physicist took this conclusion to its furthest extreme. He looked at the wave function. He looked at the measurement problem. And he asked a simple question. What if the wave function never collapses at all? Every quantum measurement has multiple possible outcomes. The standard view says reality picks one and erases the rest. Hugh Everett, in 1957, said reality picks all of them, and every possibility branches into its own world. He was 27 years old. He was a graduate student at Princeton. He proposed that the universe splits again and again every time a quantum event occurs. His advisors hated it. He left academia and went to work for the Pentagon. But the idea did not die. It grew. The many worlds interpretation starts from a simple observation. The Schrödinger equation, the equation that describes quantum systems, has no collapse in it. The math says the wave function evolves smoothly, forever. Collapse is added by hand. It is the awkward patch that makes the theory match what we see. Everett asked what happens if you take the math seriously. If you remove the patch, if you trust the equation, the answer is that there is no collapse. There is no single outcome. Every possibility continues to exist. And the reason we only see one of them is that we, the observers, also become part of the wave function. We split along with everything else. When you measure an electron's spin, the universe does not choose. Two versions of you appear. One sees spin up, one sees spin down. Both are real. Both think they are the only one. Each one continues from there, branching again at every future quantum event. The result is a tree, an endless branching tree of universes. Every possible outcome of every possible event, somewhere, happens. In one branch, you took a different job. In another, you never met the people you love. In another, the dinosaurs were never wiped out. In another, the universe cooled too fast for galaxies to form. It sounds like science fiction. It is taken seriously by some of the most respected physicists alive. Physicists like David Deutsch, Sean Carroll, and Max Tegmark have written extensively about why the math may demand it. The advantage of many worlds is that it removes the measurement problem entirely. There is no mysterious collapse. There are no special observers. The quantum and classical worlds are unified. The wave function is all there is, and it never stops evolving. The disadvantage is that it requires accepting an unimaginable number of parallel realities. Every photon scattering off your skin creates new branches. Every air molecule jostling in the room creates more. The total number of universes, if many worlds is correct, grows beyond anything the human mind can hold. And here is the unsettling question. If every possible outcome happens somewhere, is there a version of you that is reading this right now, and a version that is not? Is there a version that lived a different hour? A version that died yesterday? A version that was never born? The math does not say this is metaphor. The math says these worlds are as real as the one you are in. Critics argue that many worlds is unfalsifiable. We cannot communicate with the other branches. We cannot test for them. Some say this makes it philosophy, not physics. Others argue that the math is so clean, so free of contradiction, that the burden of proof should fall on those who add a collapse to it. The debate is unresolved. The interpretation remains live. What is certain is this. If many worlds is correct, the universe is far stranger than anyone imagined. But it gets stranger still. Some physicists now suspect that the universe we see is not even the most fundamental layer. That what we call reality is a projection. a signal, a surface effect of something deeper. They suspect we may be living inside a simulation. Physics has begun to ask a question that used to belong to science fiction. Are we living inside a computer? The strange part is that the question is no longer easy to dismiss. Several lines of evidence point in an uncomfortable direction. The simulation hypothesis was sharpened in 2003 by philosopher Nick Bostrom. He argued that if any civilization ever became advanced enough to run detailed simulations of conscious beings, they would likely run many of them. Far more simulations than original universes. Statistically, then, any conscious being should expect to be inside a simulation rather than outside one. That argument is philosophical. What is new is that physics has started finding hints that look strangely like simulation artifacts. The first hint is the discreteness of space-time. At the smaller scale, distance itself appears to come in fixed units. The Planck length, about 1/10 trillionth of the size of a proton, may be the smallest possible step in space. Below it, the very idea of distance breaks down. Some physicists think this is just a feature of quantum gravity. Others note that it looks remarkably like the resolution of a screen. Reality might have pixels. The second hint is the speed of light. Every signal in the universe is bound by it. Nothing exceeds it. Information itself cannot move faster. In computer simulations, similar limits exist for a practical reason. The simulation can only update at a finite rate. There is a refresh limit. The third hint is the strange efficiency of physical law. The mathematics that describes the universe is shockingly compact. The standard model of particle physics fits on a single page. General relativity fits on a postcard. The deeper physicists look, the more the universe seems to behave like a system optimized for computation, not a sprawl of arbitrary rules. The fourth hint comes from quantum mechanics itself. Particles do not have definite values until they are measured. This is exactly how a well-designed simulation would work. There is no need to render details that no one is looking at. Reality only commits to specifics when an observer interacts. In 2017, physicists at the University of Oxford and the Hebrew University of Jerusalem published a paper showing that simulating certain quantum systems would require so much computing power that no classical computer could ever do it. They concluded that if our universe is being simulated, it cannot be on a regular machine. The simulator would have to be quantum itself. That does not rule out the hypothesis. It only narrows the kind of computer needed. Other physicists have proposed direct tests. If reality is a simulation with a finite resolution, certain very high-energy cosmic rays should show small deviations from the predictions of standard physics. Searches are ongoing. Nothing conclusive has appeared yet. Nothing has ruled it out either. Here is the disquieting part. The simulation hypothesis is not just a story. It is one of the few ideas that explains, in a single stroke, the strange features of quantum mechanics, the fine-tuning of physical constants, and the mathematical neatness of natural law. It would also mean that everything around you, including the thoughts in your head, is data, patterns, code being run on a substrate we cannot reach. Most physicists do not believe the universe is literally a simulation, but few will say it is impossible. The question has moved out of philosophy and into the edge of testable science. And one related idea has gone further. It says the three-dimensional world we see may not be fundamental at all. It may be a projection from a flat surface, far away, where the real information is stored. The universe, in this view, is a hologram. Look at your hand. It has depth, width, length. It feels solid. It feels three-dimensional. Some physicists now believe none of that is fundamental. The depth is an illusion. Your hand and everything else may be a projection. The real information lives on a flat surface at the edge of the universe. This is the holographic principle, and it began with a black hole. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking made a strange discovery about black holes. The amount of information a black hole could hold was not proportional to its volume, as you might expect. It was proportional to its surface area, to the size of the event horizon. The two-dimensional boundary, not the three-dimensional interior. That seemed wrong. A bigger interior should hold more stuff. But the math kept saying the limit lived on the surface. In 1993, the Dutch physicist Gerard 't Hooft pushed this further. He proposed that maybe all information in any region of space is encoded on its boundary. The interior is just a kind of readout, a holographic display. A year later, the American physicist Leonard Susskind extended the idea to the entire universe. If 't Hooft was right, then the three-dimensional cosmos we live in is a projection of information stored on a two-dimensional surface, far away. For years, this was a wild idea. Then, in 1997, the Argentine physicist Juan Maldacena proved a precise version of it. He showed mathematically that a particular kind of universe, with a certain shape, is exactly equivalent to a quantum theory living on its boundary. The interior physics and the boundary physics describe the same thing. They are different languages for the same reality. This is called the ADS/CFT correspondence, and it is one of the most important results in theoretical physics in the last 50 years. The version Maldacena proved is not exactly our universe. Our universe has a slightly different shape. But the core idea, the principle that information in a volume can be fully captured on its surface, has held up. Many physicists now suspect that some form of the holographic principle applies to reality itself. If they are right, the implications are dizzying. Depth, distance, volume, the very fabric of three-dimensional space may be emergent. They may not be fundamental features of nature. They may be the way our minds, embedded inside the system, interpret a flat sheet of information. You are not really three-dimensional. You are the shadow of something flat. The light, the pixels, the data on the boundary. There is direct experimental interest in this now. A program called the Holometer, run at Fermilab in Illinois, was designed to look for holographic noise, tiny fluctuations in space-time that would appear if reality is projected from a finite resolution surface. The first results, published in 2015, did not find the predicted noise, but the search continues with more sensitive instruments, and other proposed tests are being explored. The holographic principle does something quietly devastating. It tells us that our intuition about space, the most basic feeling we have about the world, may be deeply wrong. Distance might not exist the way we think. Volume might be a coding trick. The inside might be the outside, dressed up in a language our brains evolved to speak. This idea connects to one of the deepest unsolved problems in modern physics. A paradox first noticed at the edge of black holes. A paradox about what happens to information when it falls in. That paradox has nearly broken physics 3 times. A book falls into a black hole. The pages, the words, the patterns of ink, all of it crosses the event horizon and disappears from view. Decades pass. The black hole slowly evaporates, leaking energy back into the universe. Eventually it is gone, and so is the book. The question is simple. Where did the information go? The answer should also be simple. Physics has a sacred rule called unitarity. Information is never destroyed. Every state of the universe contains, in principle, all the information needed to reconstruct what came before. The universe does not forget, but black holes seemed to forget. Stephen Hawking proved this in 1975. He showed that black holes do not just sit there, they radiate. The radiation comes from quantum effects near the event horizon, and over enormous spans of time, this radiation drains the black hole away to nothing. The radiation he predicted is now called Hawking radiation. Here is the problem. The radiation, according to his calculations, is purely thermal, random. It carries no specific information about what fell in. The book, and everything that ever crossed the horizon, is destroyed forever. This contradicted unitarity. The 2 pillars of modern physics, quantum mechanics and general relativity, gave directly opposite answers about what happens. One said information must be preserved. The other said information must be lost. They could not both be right. The conflict became known as the black hole information paradox. Hawking himself initially believed information was truly destroyed. He famously made a bet with the physicist John Preskill in 1997 that information was lost. In 2004, Hawking conceded the bet. He had come to believe that information was preserved after all, though the mechanism was unclear. He paid Preskill with a baseball encyclopedia, joking that information could be extracted from it only with great effort. For the next decade, the paradox remained a deep wound in physics. Then, between 2019 and 2020, a series of breakthroughs began to resolve it. Physicists, including Jeff Pennington and a team led by Ahmed Almheiri, found a way to calculate the entropy of Hawking radiation more carefully. They used techniques borrowed from the holographic principle and a tool called the quantum extremal surface. The result showed that information does come back out of the black hole, smuggled in subtle correlations within the radiation. The book is not destroyed. It is shredded, scattered, and slowly returned, photon by photon, over the lifetime of the black hole. To recover the book, you would need to collect all of the radiation and decode it. In practice, this is impossible. In principle, the information is there. This rescue came at a cost. The math suggests that to make it work, the inside of a black hole and the outside are connected in strange ways. The inside, at some level, may not be a separate region. It may be encoded in the same information that drifts away as radiation. This is called the island formula, and it remains an active area of research. The full picture is not yet settled, but the larger lesson is clear. Information is sacred. Even black holes, the most extreme objects in the universe, cannot truly erase it. What this means for the rest of physics is enormous. It implies that space, time, and information are stitched together in ways we are only beginning to map. It hints that the inside of a black hole may not exist as we imagine it, and it raised an even harder question. If information escapes through Hawking radiation, what exactly is happening at the edge of the black hole? The answer was a wall made of fire. Stephen Hawking sat in his wheelchair in Cambridge in 1974 and quietly destroyed 2 centuries of physics. He had been studying black holes using the rules of quantum field theory. According to general relativity, nothing escapes a black hole. Not light, not matter, nothing. The event horizon is supposed to be a one-way door. Hawking found a leak. The leak comes from the strange behavior of empty space. According to quantum theory, the vacuum is not truly empty. It is full of pairs of virtual particles popping into existence and annihilating each other almost instantly. This is real. It has been measured. It produces tiny effects called the Casimir force, observed in the lab. Now move that vacuum to the edge of a black hole. A pair of virtual particles flickers into being right at the event horizon. One falls in, the other escapes. The escaping particle becomes real. It carries energy away from the black hole. The infalling particle, in a sense, takes negative energy inward, reducing the black hole's mass. Over staggering amounts of time, this trickle of escaping particles drains the black hole entirely. A black hole the mass of our local star would take far longer than the current age of the universe to evaporate. A small one could vanish quickly. Either way, the result is the same. Black holes are not eternal, they die, slowly, glowing softly into the dark until they are gone. This radiation is named after Hawking. It is one of the most celebrated predictions in modern physics. It has not yet been directly observed in space because the radiation from real black holes is far too faint to detect against the background of the universe. But analog versions have been seen. In 2016, Jeff Steinhauer at the Technion in Israel created a sonic black hole using ultra-cold atoms. He set up a fluid that flowed faster than the speed of sound in its own medium. Sound waves on the slow side could not catch up to the boundary. It became an acoustic event horizon. And he measured the equivalent of Hawking radiation leaking out. Sound where there should have been silence. The experiment matched the predictions. Hawking's calculation, decades old, pointed exactly where to look. Hawking radiation forces a confrontation. It says black holes are temporary. It says they emit. It says the universe has a built-in mechanism to slowly unwind even its most extreme structures. But it left the information problem wide open. The radiation, in Hawking's original calculation, looked random. If the radiation carries no specific information about what fell in, then the act of falling in destroys data. That destruction is what physics cannot accept. For decades, this was the wound. Hawking's calculation was too clean to ignore and too disturbing to accept. Physicists tried every escape route. Maybe the information leaks out in subtle correlations. Maybe it is stored at the horizon. Maybe it is hidden in the final flash of evaporation. The recent results in the holographic program suggest the answer is some combination of these. The information is encoded in the radiation, but in correlations too entangled to read without a complete picture. And this is where it gets stranger. The new calculations seem to require something that violates a basic principle of relativity. Something must happen at the event horizon that does not match what general relativity says you would experience falling in. Some physicists proposed a solution so violent that it became one of the most disturbing ideas in modern physics. They called it the firewall. You drift toward a black hole feet first. The event horizon is just ahead. According to Einstein, you should feel nothing as you cross it. The geometry is smooth. Space and time are continuous. The horizon is a place where the math changes meaning, but locally it is calm. In 2012, 4 physicists wrote a paper claiming this is wrong. They claimed that the moment you touch the horizon, you burn. The paper was by Ahmed Al-Mahiri, Donald Marolf, Joseph Polkinski, and James Sully. They argued that to make the black hole information problem consistent with quantum mechanics, the event horizon must be replaced by a wall of intense radiation, a firewall, an incinerating sheet of high-energy particles that destroys anything that reaches it. The argument is technical, but the core is sharp. There are 3 principles physicists hold dear. Information must be preserved. The laws of physics must be the same everywhere, including for an observer falling into a black hole. And quantum entanglement has limits. A particle cannot be maximally entangled with 2 other things at the same time. These 3 rules, applied to the radiation leaking out of a black hole and the particles still inside, do not all fit. One of them must break. The firewall paper argued that the principle that breaks is the smooth horizon. The infalling observer does not glide gently across. They collide with a wall of fire. This was a catastrophe for physics. General relativity is one of the most accurate theories ever developed. It has been confirmed in every test. The smooth horizon is one of its core predictions. If it fails, then Einstein's picture of black holes and of gravity itself is incomplete. The community was split. Some physicists accepted firewalls as the price of saving quantum mechanics. Others searched for ways to keep the horizon smooth. The most striking proposal came from Leonard Susskind and Juan Maldacena. They argued that the firewall could be avoided if the radiation outside the black hole and the particles inside it are connected by something stranger. Something that links distant points of space directly. They proposed a wormhole, not a metaphorical wormhole, a real mathematical bridge through space-time. Every entangled pair, in their view, is connected by a tiny wormhole. The radiation that escapes a black hole is still tied, geometrically, to what fell in. The horizon stays smooth because the inside and the outside are not really separate. This idea, called ER equals EPR, will return next. The firewall debate is not yet resolved. Recent calculations using holographic methods suggest that something close to a firewall does form, but not at the horizon. It forms much later, deep inside the black hole, after enough information has leaked out. That place is called the inner horizon. It may be a true wall of fire, hidden inside every black hole that ever existed, slowly building as the radiation escapes. You would not feel it crossing the outer edge. You would die long after, deep inside, at a place no signal can ever reach. The firewall paradox showed something that physicists had been afraid to admit. Even the smoothest, cleanest predictions of relativity may not survive contact with quantum mechanics. The 2 theories at the edges of black holes do not agree on what space itself is. To stitch them together, physicists are now exploring an idea that sounds like a fairy tale. They believe the connection between distant points in space might be made of the same stuff as quantum entanglement. Reality, at the deepest level, may be sewn together by invisible threads. In 1935, Albert Einstein wrote 2 papers that shook physics. One was about wormholes, bridges through space-time called Einstein-Rosen bridges, that could in theory connect 2 distant points instantly. The other was about entanglement, pairs of particles that share a single quantum state across any distance. For 80 years, the 2 ideas were treated as unrelated. One was geometry, one was quantum strangeness. In 2013, 2 physicists proposed they were the same thing. Leonard Susskind and Juan Maldacena published a short paper with a now famous title, ER equals EPR. The ER stands for Einstein-Rosen, the wormhole. The EPR stands for Einstein-Podolsky-Rosen, the original 1935 paper that introduced quantum entanglement. Their claim was this: every pair of entangled particles is connected by a tiny wormhole. Geometry and entanglement are not separate phenomena. They are 2 languages for the same underlying reality. The implications are staggering. If they are right, then the structure of space itself, the very fabric we think of as the stage on which physics unfolds, is built from quantum entanglement. Distance is not fundamental. It is a side effect. 2 points are close together when they are highly entangled. 2 points are far apart when their entanglement is weak. This idea solves the firewall problem in a clean way. The radiation escaping a black hole is entangled with the particles inside. According to ER equals EPR, that entanglement is a wormhole. The inside and the outside are still connected. The horizon does not need to burn. The connection is geometric, even if we cannot see it. The proposal sits at the frontier of theoretical physics. It is not yet proven, but evidence has been accumulating. In 2015, physicists ran calculations showing that simple toy universes with the right kind of entanglement structure naturally produce wormhole-like geometries. The math fits. The pattern matches. In 2022, a team led by Maria Spyropoulou at the California Institute of Technology used Google's quantum computer Sycamore to simulate a tiny wormhole. They created a system of entangled qubits and watched information appear to traverse a holographic structure that behaved exactly like a wormhole would. The result was published in Nature. It was carefully phrased. They had not built a wormhole in physical space. They had created a quantum system whose math is identical to a wormhole. That distinction matters, but the point is that the math works. The deep equivalence between entanglement and geometry is not just speculation. It can be tested in the lab. If this picture is right, then the universe is held together in a way no one expected. Every grain of space, every patch of vacuum, every cubic millimeter of empty room is woven from quantum threads. Space-time is not a stage. It is a fabric. The fabric is made of entanglement. Cut the entanglement, and the fabric tears. Some physicists now believe that this is the missing link between quantum mechanics and gravity. The 2 theories, separate for a century, may be united by recognizing that geometry itself is quantum. This is the project of quantum gravity, and it is one of the deepest active research efforts in the world. But ER equals EPR is one approach. There are others. Other physicists believe that space and time are not made of entanglement at all. They are made of something even more fundamental. They believe space-time is built from tiny, indivisible chunks, loops, a web of interlocking pieces too small to see, and those loops would change everything. You can divide a meter in half, then in half again, and again. Most of us assume this can go on forever. Space is smooth, continuous, endlessly cuttable. A growing field of physics says no. Loop quantum gravity, developed since the 1980s by physicists like Carlo Rovelli, Lee Smolin, and Abhay Ashtekar, proposes that space comes in pieces. There is a smallest possible unit of volume, a smallest possible unit of area. Below it, the very idea of space breaks down. The smallest meaningful length is the Planck length, about 100 trillion times smaller than a proton. The smallest meaningful time is the Planck time, the duration light takes to cross a Planck length. According to loop quantum gravity, these are not just convenient numbers, they are actual limits. Reality at its base is discrete, pixelated, made of indivisible chunks, stitched into a network. The picture they describe is called a spin network. Imagine a vast tangle of nodes connected by lines. The nodes are tiny units of volume. The lines are units of area. Together they form the fabric of space. What we call empty space is, in this view, an enormous lattice of these chunks, knitting themselves into the smooth-looking room around you. Time, in loop quantum gravity, is just as discrete. It does not flow. It ticks. Each tick is a Planck time. Each tick advances the spin network into a new configuration. The history of the universe is a sequence of these snapshots, woven together into what we experience as duration. If this is right, the universe is fundamentally a kind of relational machine. There is no smooth background. There is no continuous time axis. There is only a vast network of discrete pieces, evolving step by step. There is a real test to look for. Light traveling enormous distances should pick up tiny signatures of the underlying discreteness. If space-time is made of pixels, photons of different energies should travel at very slightly different speeds. The effect would be vanishingly small, but over billions of light years, it could add up to a measurable delay. Astronomers have been searching. Gamma-ray bursts from distant galaxies are studied for any sign of this. So far, no clear signal has emerged. Some results suggest the effect, if it exists, is even smaller than predicted. Others leave room for a discrete space-time at scales we cannot yet measure. Loop quantum gravity also makes a startling prediction about black holes. The singularity at the center, the point of infinite density that general relativity predicts, does not exist. The discreteness of space prevents infinite compression. Matter falling into a black hole cannot be crushed beyond the Planck scale. Instead, the math suggests it bounces. The collapse halts, then it reverses. Slowly, over enormous timescales, the black hole transforms into a kind of white hole, releasing its contents back into the universe. This has not been observed. It would happen far too slowly for any black hole we have yet seen. But it is a real prediction. Some physicists are looking for the signatures of these bounces in the early universe, in case some primordial black holes have already completed the cycle. If loop quantum gravity is correct, the universe is a vast ticking weave of tiny chunks. Smooth space is an illusion. Continuous time is the story we tell at scales much larger than reality's pixels. But there is another approach, a rival theory, one that has been building for 50 years and predicts not just discrete space, but 11 dimensions, vibrating filaments of energy, and a hidden mathematical structure underlying every particle that exists. It is called string theory, and it may be the deepest map we have of the universe yet drawn. Look closely enough at any particle, a quark, an electron, a photon. According to string theory, you would not find a tiny ball. You would find a vibrating string, a loop of energy, smaller than anything we can ever see, and every particle in the universe is made of these strings. String theory began in the late 1960s as an attempt to understand the strong force inside atomic nuclei. It quickly became something larger. Researchers realized that if the basic objects of nature are not points but strings, the math automatically includes gravity. The graviton, the hypothetical particle that carries the gravitational force, falls naturally out of the equations. No other approach to quantum gravity gave it for free. This was a massive clue. It suggested that string theory might be the long-sought unified theory, the framework that joins quantum mechanics and general relativity into a single description of nature. But the math came with a strange demand. The equations only work if the universe has more than 3 spatial dimensions. The earliest versions required 26. Refined versions settled on 10. Modern string theory, sometimes called M-theory, requires 11 dimensions. 3 of space, 1 of time, 7 extra dimensions, hidden, curled into shapes too small to ever observe directly. The picture is something like this. Every point in space is not a point. It is a tiny, twisted ball with 7 extra directions tucked inside it. They are too small for anything we can build to detect. Curled at scales far below the Planck length, they shape the laws of physics at the macroscopic level we live in. The vibrations of strings in these hidden dimensions determine which particles exist and how they interact. This sounds ridiculous. It is not. The math has been carefully developed for decades. It has produced striking results, including new insights into black holes, quantum gravity, and the structure of space-time. The holographic principle that we explored earlier was discovered through string theory. But there is a problem. String theory has not made a single prediction that has been experimentally verified. The energies needed to see strings directly are far beyond anything our particle accelerators can reach. We would need a machine the size of a galaxy. The lack of testable predictions has led some physicists to argue that string theory is no longer science. Others defend it as the most mathematically elegant framework ever developed. The debate is sharp. What makes string theory genuinely strange, though, is not the dimensions. It is the multiverse it implies. The number of possible ways the extra dimensions can be curled is enormous. Each different curling produces a different set of physical laws. Different particles, different forces, different universes. Estimates suggest there are something like 10 followed by 500 zeros possible configurations. This is called the string theory landscape. Each point in the landscape is a different possible universe. If string theory is correct, then our universe is one configuration out of an astronomical number. The reasons our laws of physics look the way they do may be no more profound than the reason a coin lands heads. We are simply in one of the universes where the curling produces beings that can ask the question. This idea connects directly to a deeper one. If our universe is one possibility, what about the others? Do they exist somewhere? Or are they only mathematical possibilities, never realized? The answer, according to one of the most ambitious cosmological theories of the past 40 years, is that they all exist. The universe is not alone. It is one bubble in an endless ocean. And that ocean is still expanding. 14 billion years ago, the universe expanded faster than light for a fraction of a second. Space stretched at a rate so extreme that 2 points originally next to each other ended up separated by distances larger than the observable cosmos. This is called inflation. It is the leading theory for what happened in the first instant after the Big Bang. It explains why the universe looks so uniform across vast distances. It explains the patterns we see in the cosmic microwave background, the faint glow left over from the early universe. It has been confirmed, in its broad outlines, by satellites including WMAP and Planck. But the theory has a strange implication. Inflation, once started, may never fully stop. This is called eternal inflation, proposed by physicists Andrei Linde, Alexander Vilenkin, and others in the 1980s. The idea is that the inflating field that drove the early expansion does not end smoothly. It ends in patches. In some regions of the inflating space, quantum fluctuations cause the field to slow and stop. Those regions become normal universes, cooling, forming particles, evolving into something like the cosmos we see. But the rest of the field keeps inflating. New patches stop, new universes are born. The space between them keeps stretching, faster than they can grow. The result is a vast, branching structure of pocket universes, each one its own bubble, separated from every other by infinite stretches of still inflating space. This is the multiverse, not the parallel worlds of many worlds quantum mechanics. A different multiverse, a spatial one, a landscape of distinct universes, each born from the same mother field, separated forever by the relentless expansion of space between them. If this picture is right, our universe is one bubble. The Big Bang, we know, is just one freeze-out event in a much larger ocean. The other bubbles are out there, real, beyond any signal we could ever send or receive. Their light will never reach us. Their inhabitants, if any, will never know we exist. And here is where it joins string theory. If string theory is correct, each pocket universe could end up with a different configuration of the extra dimensions, different physical laws, different particles, different constants of nature. Some bubbles have universes where stars never form. Some have no chemistry. Some collapse before they can develop anything. Some, by sheer chance, settle into a configuration like ours, with laws fine-tuned by accident for atoms, planets, and life. We exist in one of the rare ones that work. This is sometimes called the anthropic explanation. The universe looks fine-tuned because we could only exist in a fine-tuned one. The other bubbles, the ones that failed, have no observers asking the question. The multiverse is one of the most controversial ideas in physics. Critics argue that since we cannot detect the other bubbles, the theory is unfalsifiable. They worry it ends physics as a predictive science. Defenders argue that the multiverse is not a postulate. It is a consequence of two theories we have good reasons to take seriously. Inflation explains the universe we see. String theory may unify the forces of nature. Together, they suggest a multiverse, whether we like it or not. There may be small, indirect tests. If our bubble universe has ever collided with another, the impact might leave a faint imprint in the cosmic microwave background. Searches for such bubble collision signatures have been carried out. So far, nothing definitive has been found. If eternal inflation is correct, then everything we know is one chapter in a book of infinite chapters. Most chapters are unwritten because their universes never developed observers. In ours, observers did develop, and the moment they looked closely at the universe, they found something that should be impossible. It looked too still. It looked too quiet. It looked like it was waiting to fall. The universe may be sitting on a cliff. It looks stable. It feels stable. We have walked across its surface for billions of years without falling. But the math says we may not be on solid ground at all. We may be on a ledge. And the real bottom is somewhere far below. This is called vacuum decay. And it is one of the most disturbing predictions in modern physics. The idea begins with a quiet object called the Higgs field. The Higgs field fills all of space. It is what gives particles their mass. Every electron, every quark, every atom in your body owes its weight to its interaction with this invisible field. The Higgs particle, discovered at the Large Hadron Collider in 2012, was the proof that the field is real. Once physicists measured the Higgs particle's mass, they could calculate something else: the shape of the Higgs field's energy landscape, the places where it sits stably, the places where it does not. The result was alarming. The Higgs field appears to be in a metastable state. It looks stable, it acts stable, but the math suggests there is a deeper, lower energy state somewhere else, a truer vacuum, and nothing in the laws of physics prevents the universe from finding it. The transition would happen by quantum tunneling. Somewhere in some random patch of space, a tiny bubble of the true vacuum could spontaneously appear. Inside the bubble, the laws of physics would be different. Particles would have different masses. Atoms might no longer hold together. Chemistry would unravel. The bubble would expand at nearly the speed of light. It would consume everything in its path. There would be no warning. No light would reach us before the bubble itself arrived. By the time you notice, you would already be inside it. Or rather, you would not. Because nothing recognizable would survive the transition. This is the end of the universe in its most absolute form. Not a slow heat death over trillions of years. Not a collapse into a final crunch. A sudden, instantaneous rewriting of physical law, propagating outward at light speed, leaving a different universe behind. The good news, if you can call it that, is that the probability is tiny. Calculations suggest the lifetime of our current vacuum is longer than the current age of the universe, by a staggering factor. The chance of a bubble forming in any given lifetime is vanishingly small. We are statistically safe. The bad news is that the chance is not zero, it is real, and it could happen anywhere. There may already be a bubble racing toward Earth right now, expanding at light speed, invisible until it arrives. There is some debate about whether the calculations are accurate. The metastable result depends on extrapolating known physics to extreme energies. Unknown particles, unknown forces, or quantum gravity effects could change the picture entirely. Some physicists believe the universe is fully stable, and the metastable result is an artifact of incomplete theory. But several careful analyses, including a major study published in 2018 by physicists using the latest measurements of the Higgs and the top quark, have confirmed the metastable conclusion. With the data we have, our vacuum is not the lowest possible state. This raises a strange question about meaning. We exist on borrowed time in a universe that might not be its own final form. The stars, the galaxies, every fact we have ever known may be footnotes on a temporary version of reality. The deeper unease is that vacuum decay points to something even older than the question of when the universe ends. It points to the question of why it has the properties it does at all. That question opened a wound in physics that no one has ever closed. There is a number in physics that should not be what it is. It is off, not by a little, but by the largest discrepancy ever recorded between theory and observation. The number is the cosmological constant. It describes the energy of empty space. When physicists calculate using the rules of quantum field theory, how much energy should be in a vacuum, the answer comes out enormous. The vacuum should be teeming with energy. Every cubic centimeter of empty space should contain an amount of energy that would make the universe explode outward at unimaginable rates. Galaxies could never form. Stars could never burn. Atoms could never hold together. When astronomers actually measure the energy of empty space by watching the expansion of the universe, the answer is very different. There is energy there, but it is small, inconceivably small. The disagreement is roughly 1 followed by 120 zeros. The theoretical prediction is that much larger than the measurement. This is not a small error. It is the worst prediction in the history of science. Physicists call this the cosmological constant problem. It is, by some accounts, the deepest puzzle in modern physics. Here is what makes it stranger. The energy of empty space is not zero. It is not negligible. It exists. We know this because in 1998, 2 teams of astronomers using distant supernovae as standard candles discovered that the expansion of the universe is accelerating. Something is pushing space apart faster and faster. That something is the energy of the vacuum. It has been named dark energy, and it makes up about 70% of everything in the universe. But the amount is tiny compared to what theory predicts. The vacuum energy is real. It is just absurdly weaker than it should be. Why? Why is the cosmological constant the value it is? Not zero. Not catastrophically large. Sitting at a perfectly tuned, perfectly small number that allows galaxies to form, stars to live, planets to cool, and life to emerge. There is no agreed answer. Some physicists invoke the multiverse. If there are infinitely many universes with different cosmological constants, we naturally find ourselves in one where the value happens to be small enough for observers to exist. Most universes are uninhabitable. Ours is one of the rare exceptions. Others suspect there is a hidden mechanism, a symmetry, a deeper principle that forces the vacuum energy to take its specific, tiny value. The mechanism has not been found. Still others suspect the calculation itself is wrong, that the way we estimate vacuum energy in quantum field theory is not the right tool, that something fundamental about how to combine quantum mechanics and gravity is missing. A few proposals try to make the constant evolve over time. Some invoke new fields, some invoke modified gravity. None of these has been experimentally confirmed. The discomfort runs deep. The cosmological constant is a number that, if it had been only slightly larger, would have prevented galaxies from forming. If only slightly smaller or negative, the universe would have collapsed long ago. The window for life is vanishingly thin, and nature appears to have threaded that window precisely. We are sitting inside a coincidence so large that it might not be a coincidence at all. The dark energy that emerged from this puzzle, the small but real vacuum energy, is now driving the universe apart. It is the dominant force shaping the long-term future of the cosmos. Every billion years, more galaxies recede beyond our reach, and the way it is doing so is not gentle. It is winning. Galaxies are running away from us. The further they are, the faster they flee. This was discovered nearly a century ago by Edwin Hubble. For decades, physicists believed that gravity would slow this expansion. Eventually, the universe would coast, possibly even collapse. In 1998, two teams of astronomers found something that froze the field. The expansion is not slowing, it is accelerating. The teams were led by Saul Perlmutter, Brian Schmidt, and Adam Rees. They used a particular kind of exploding star, called a Type 1 supernova, as a cosmic mile marker. These supernovae always explode with nearly the same brightness, which means their distance can be measured precisely. By comparing their distance to how fast the galaxies hosting them were moving away, the teams could trace the expansion history of the universe. The result contradicted every prediction. Distant supernovae were dimmer than they should have been. The galaxies were further away than expected. The universe was not slowing, it was speeding up. The three astronomers shared the Nobel Prize for this discovery in 2011. The implication was clear. Some unknown form of energy is pushing the universe apart, and it is winning against gravity. This unknown energy got a name: dark energy. The name is honest. It signals that we know it is there, but we do not know what it is. What we do know is its scale. Dark energy makes up about 68% of the total contents of the universe. Ordinary matter, the stuff of stars, planets, gas, and people, is only about 5%. The rest is dark matter, which we will return to soon. Dark energy is the largest single component of the universe, and we do not know what it is made of. The simplest explanation is that dark energy is the cosmological constant, the energy of empty space itself, vacuum energy, the same energy whose theoretical value disagrees with observation by an absurd amount. If this is correct, then dark energy will continue forever. As space expands, more space comes into existence. More space means more vacuum. More vacuum means more energy driving the expansion. The cycle accelerates. The long-term future of such a universe is bleak. Galaxies will keep accelerating away from each other. In tens of billions of years, the night sky from our planet will look emptier. Distant galaxies will redshift beyond visibility. Cosmologists in some far future civilization, looking up, would see only their own galaxy. The rest of the universe will have vanished from sight. There are alternative ideas. Some theories propose that dark energy is not a constant but a slowly changing field. Others suggest gravity itself behaves differently at very large scales, mimicking the appearance of dark energy without it actually existing. Recent results from the Dark Energy Spectroscopic Instrument, a telescope project mapping millions of galaxies, hinted in 2024 and 2025 that dark energy might not be perfectly constant. The hints are early and not yet conclusive. If confirmed, they would suggest the energy is changing over cosmic time. That would change the long-term future of the universe in ways we cannot yet predict. Dark energy, in any form, is a puzzle of breathtaking scale. It dominates the universe. It will determine its fate. And we cannot say what it is. The discovery of dark energy was the second major detection of something we cannot see. The first came earlier, and in some ways it is even harder to explain. The universe contains far more matter than the matter we can detect. And whatever it is not made of atoms. Galaxies should fly apart. They spin too fast to hold themselves together with the gravity of their visible matter. Stars at the edges of spiral galaxies orbit at speeds that should fling them out into intergalactic space, yet the galaxies hold. They have held for billions of years. Something is gripping them. Something we cannot see. This is dark matter. And the case for it has been building since the 1930s. The Swiss astronomer Fritz Zwicky was the first to notice. He studied the Coma Cluster, a group of galaxies bound together by their mutual gravity. He measured how fast they were moving. They were moving so fast that the visible matter could not possibly keep them together. There should be far more mass than telescopes could detect. He called the missing material Dunkle Materie, dark matter. The German term has stuck. For decades, his work was largely ignored. Then, in the 1970s, the American astronomer Vera Rubin made measurements that could not be denied. She studied the rotation of dozens of galaxies. The pattern was always the same. Stars at the outer edges moved as fast as stars near the center. This is impossible if galaxies are made only of what we can see. There must be a vast halo of invisible matter, much heavier than the visible stuff, holding everything in place. Her work was definitive. Galaxies are full of something we cannot detect with telescopes. That something is now estimated to make up about 27% of the universe. Atoms, the matter we know, make up only 5%. Dark matter outweighs ordinary matter by a factor of more than 5 to 1. It is not just hiding in galaxies. Dark matter has been mapped at far larger scales. The cosmic microwave background, the radiation left over from the early universe, contains imprints of dark matter, clumping into the structures that would later become galaxies. Surveys of the large-scale structure of the universe match the predictions of cold dark matter remarkably well. The Bullet Cluster, two galaxy clusters that collided, shows visible matter in one place and the gravitational center of mass in another. The mass is somewhere, the visible stuff is not. This is no longer disputed. Something is there. Something massive. Something that interacts only through gravity, ignoring electromagnetic radiation entirely. It does not glow. It does not absorb light. It passes through ordinary matter as if it were not there. But what is it? For decades, physicists searched for a particular candidate. A heavy, weakly interacting particle that would naturally appear in extensions of the Standard Model. Experiments deep underground, shielded from cosmic rays, watched for the rare flash of a dark matter particle bumping into a sensitive detector. Many experiments, many decades, almost nothing. The leading candidates have been gradually ruled out. The simplest models do not fit the data. Researchers have moved on to other possibilities. Lighter particles, heavier particles, strange new fields, black holes left over from the Big Bang, modifications to gravity itself. None of these has yet been confirmed. The hunt continues. What is striking is the scale of our ignorance. The dominant form of matter in the universe is not the matter we are made of. The universe is mostly something else. Galaxies are scaffolded by invisible halos. The structure of the cosmos was sculpted by particles we cannot identify. This points to a deeper puzzle. The constants of nature, the masses of particles, the strengths of forces, the values that govern reality, all sit in a narrow window that allows complex structures to form. Change them slightly. The window closes. This is the fine-tuning problem. And no one knows why we got lucky. The universe should not work. Not as well as it does. Not for life, not for stars, not even for atoms. Physicists have catalogued a list of physical constants that govern reality. The strength of gravity. The strength of the strong nuclear force. The mass of the electron, the mass of the proton, the cosmological constant. About 24 numbers in total that determine what kind of universe you get. Each of those numbers, if changed even slightly, would produce a universe with no stars, no atoms, no chemistry, no possibility of life as we understand it. The strong force binds quarks into protons and neutrons. If it were a few percent weaker, atomic nuclei would not hold together. Hydrogen would be the only element. Stars would be impossible. If it were a few percent stronger, hydrogen itself could not survive. All the hydrogen would have fused into helium in the early universe. Stars would have nothing to burn. Water could not exist. Gravity is similarly delicate. Stronger gravity and stars burn out faster than life can develop on any planet around them. Weaker gravity, and stars never ignite at all. Either way, no carbon, no life. The mass of the electron is another. Slightly heavier, and stable atoms break apart. Slightly lighter, and chemistry as we know it disappears. The cosmological constant, as we have already seen, sits at a value vastly smaller than theory predicts. If it were larger by even a tiny amount, galaxies could never have formed. If it were negative, the universe would have collapsed long before life had a chance. There are many such examples. Each constant, examined in isolation, looks finely tuned. The universe, taken as a whole, looks like a watch built to extraordinary precision, with every gear set to allow for atoms, stars, and observers. Why? This is the fine-tuning problem. It is one of the most uncomfortable puzzles in physics. There are roughly 4 kinds of answer that have been seriously proposed. The first is that we are simply lucky. The constants are what they are by some unexplained law, and we happen to live in a universe that works. This is unsatisfying. The improbability is too large. The second is the multiverse explanation. If there are countless universes, each with different constants, then naturally observers will only find themselves in the rare ones that work. Most universes are dead. We are in a live one because we exist to ask the question. This is the anthropic principle. It is logically sound, but it is also extremely difficult to test, because the other universes are by definition out of reach. The third is that there is a hidden law. a deeper principle that forces the constants to take their specific values. Some physicists believe a final theory of physics will explain why the constants are exactly what they are, removing the appearance of fine-tuning. So far, no such law has been found. The fourth, and most uncomfortable, is that the universe was designed, that some intelligence selected the constants to allow for observers. This answer is mostly outside science, and most physicists reject it on methodological grounds, but it has been proposed seriously, both in religious and secular forms, and it remains a live argument in some philosophical circles. The fine-tuning is real. The explanation is not. Whichever answer you find most plausible, the fact remains. The constants of nature look chosen, either by chance over uncountable trials, by hidden law, or by something stranger. And one chilling possibility connects directly to this puzzle. A possibility that quietly suggests most observers in the universe are not human, not aliens, not anything we would recognize. They are floating brains, and they outnumber us by an unimaginable margin. Picture a vacuum. A cold, dark stretch of empty space, nothing in it, not even a single particle. Now wait long enough, and the math says something will happen. Random fluctuations in the vacuum will, very rarely, produce particles. Even rarer, those particles will arrange themselves into structures. Even rarer still, those structures will be conscious. A brain, floating in the dark, aware, briefly thinking, then dissolving back into nothing. This is a Boltzmann brain. And according to several mainstream cosmological theories, the universe contains far, far more of them than it contains real living creatures. The idea began in the late 1800s with the Austrian physicist Ludwig Boltzmann, who was thinking about the relationship between entropy and time. Entropy is the tendency of systems to grow more disordered. The universe as a whole is moving from a low entropy state toward a higher entropy one. The early universe was very ordered. The late universe will be a thin, scattered soup. But Boltzmann noted that, given infinite time, even a high entropy universe will occasionally produce low entropy fluctuations. Random arrangements that look briefly ordered. Most of these will be small. Some will be large. Statistically, a universe at thermal equilibrium will far more often produce a single brain by random chance than it will produce an entire universe with a big bang and stars and galaxies and life. This sounds like a curiosity. It became a real problem. If our universe expands forever, dragged apart by dark energy, it eventually settles into a state of maximum entropy, a vast cold vacuum that goes on forever. In that infinite vacuum, given infinite time, fluctuations will produce conscious observers, floating brains, with memories, with sensations, with the fleeting feeling of being aware. The math is brutal. The number of these random brains, integrated across infinite future time, is astronomically larger than the number of normal observers like you and me, who arose through the slow, ordered process of cosmic evolution. Statistically, then, any conscious mind should expect to be a Boltzmann brain. Not a real human. Not an evolved being. A momentary fluctuation, briefly assembled, with false memories of a coherent life. This is not a comforting thought. It is also not fringe. It is a serious problem in cosmology, discussed in major papers and debated by leading theorists. The physicist Sean Carroll has written extensively about it. The physicist Don Page has tried to constrain cosmological theories specifically to avoid producing too many Boltzmann brains. Why does this matter? Because if our standard picture of the universe predicts that most observers are random fluctuations, and we are not random fluctuations, then something is wrong with the picture. There are several possible escapes. The universe might end before enough time passes. Vacuum decay, which we covered earlier, could destroy the cold equilibrium before too many brains form. Dark energy might not be a true constant. There may be an unknown mechanism that prevents the fluctuations. Or our cosmological model itself might be incomplete in a deeper way. The dominance of Boltzmann brains might be a clue that we are missing something fundamental about how time and entropy actually work. Some physicists take this further. They argue that the fact we are not floating brains is itself evidence about what the universe is really like. If we trust our memories, our sense of continuity, our experience of being embedded in a real history, then our cosmological theories must allow that to be possible. They must rule out Boltzmann dominance. This is a strange method of doing science, using the existence of coherent thinkers to constrain theories of the universe. But it is now a real tool in cosmology. The question of why we are not random fluctuations leads directly to a deeper one. Why does time itself flow forward at all? That question has no satisfying answer. You can stir cream into coffee. You cannot unstir it. You can break a glass. You cannot unbreak it. You can grow old. You cannot grow young. Time, in our experience, has a clear direction. The past is fixed. The future is open. The present is the boundary between them. The laws of physics do not agree. This is the arrow of time problem. And it is one of the most surprising open puzzles in the field. If you write down the equations that govern motion, they work just as well played forward as played backward. The laws of mechanics, of electromagnetism, of quantum field theory are nearly time symmetric. There is no built-in direction. A movie of two billiard balls colliding looks valid running either way. The universe, at the level of fundamental law, does not seem to know which direction is forward. Yet our experience is one way. We remember the past, not the future. We see things break, not unbreak. The world has an obvious direction. Where does it come from? The standard answer is entropy. The second law of thermodynamics says that the disorder of an isolated system tends to increase. Cream mixes into coffee because there are vastly more disordered states than ordered ones. Statistically, systems drift toward disorder. The arrow of time in this view is the arrow of growing entropy. This explanation works as far as it goes, but it raises a deeper question. Why was the universe ever in a low entropy state to begin with? The early universe, just after the Big Bang, was in an extraordinarily low entropy state. Smooth, uniform, special. Nothing in fundamental physics requires this. The initial conditions of the universe are an unexplained mystery. Whatever set them up so that entropy could only go up from there. The arrow of time is a consequence of the universe starting in an unusually ordered configuration. Why? Why did it start that way? This is sometimes called the past hypothesis. It is a postulate added by hand, the same way collapse is added to quantum mechanics. We accept it because it matches what we see. we do not have a deep explanation for it. There are speculative answers. Some physicists propose that the universe is one of many, and we naturally find ourselves in one with a low entropy beginning, since complex observers can only exist in such universes. This is another version of the anthropic argument. Others suggest that the apparent low entropy of the early universe is misleading, that we are mismeasuring it because we do not know the full state of the gravitational field. Roger Penrose has argued that gravitational entropy was very low in the early universe, and the explanation lies in some yet undiscovered principle of quantum gravity. There is another disturbing possibility. The arrow of time may not be universal. It may be a local feature of our patch of cosmos. In other regions, in other epochs, time may run differently. Some theories of the multiverse suggest that universes pair up, with arrows pointing in opposite directions. From either side, the other looks like it is running backward. The most unsettling speculation is that time, as we experience it, is not fundamental at all. That the flow of time is a property of how observers process information. The universe simply contains a static collection of moments, like frames in a film. We move through them because of how memory works. The flow is in us. This idea has a name: the block universe. And it does more than threaten our sense of time. It threatens our sense of free will, of change, of becoming. It threatens the idea that anything is ever truly happening at all. Imagine the entire history of the universe as a single, four-dimensional object. Past, present, and future all there at once. Every moment that ever was, and every moment that ever will be, frozen into a vast crystal of space-time. Nothing flows, nothing happens. The universe simply is. This is the block universe, and many physicists, including most who work on relativity, take it seriously as a description of reality. The idea comes directly from Einstein's theories. Special relativity showed that simultaneity is not absolute. Two events that one observer sees as happening at the same moment, another observer, moving differently, will see as happening at different moments. There is no universal now. Different observers slice space-time differently. If there is no universal now, then there is no global present moving forward through time. The notion of a privileged moment, a flowing now, does not appear in the equations of physics. The equations describe a four-dimensional structure, with all moments equally real. You are inside this structure. So am I. So is every event that has ever occurred, or ever will occur. The Big Bang is not gone. It is still there, just at a different coordinate. The death of the universe, whatever it is also there, somewhere down the timeline, real, existing, already complete in some larger sense. The flow we experience, the sense of time passing, is, according to this view, a feature of consciousness, not of physics. We are creatures embedded in the four-dimensional block, with memories that point in one direction and anticipations that point in another. The motion is in our perception, not in the universe. This is a deeply uncomfortable picture. It implies that the future already exists in some sense, that tomorrow morning is just as real as this morning, that the moment of your death is a real point in space-time, fixed, waiting at its own coordinate. Some physicists prefer alternatives. The growing block universe says that the past and present are real, but the future is not yet. The block grows as time passes, with new moments added at the leading edge. This rescues the open future at the cost of giving back the privileged now. Other physicists take a more presentist view, saying only the present is real, with past and future as abstractions. But the equations of relativity are most natural in the block view, and experiments confirm relativity to extraordinary precision. The global positioning system has to account for relativistic effects on time to function correctly. Time really does run differently for satellites than for ground stations. There is no single absolute clock for the universe. This is where the picture deepens. If time is just another dimension of a static structure, then change is an illusion. The you who finished reading the previous chapter and the you reading this sentence are both real. They are both there. You are not flowing from one into the other. You are a four-dimensional pattern, extended across time, with consciousness located at every point along the way. Some philosophers find this picture liberating. Nothing is ever truly lost. Past moments do not vanish. They simply reside elsewhere. Others find it suffocating. If the future is fixed in the block, then free will is a kind of trick. We feel like we are choosing. The choices are already made. They are just at coordinates we have not yet reached. The block universe is not proven. It is a possible reading of relativity. There are quantum mechanical objections. Since quantum measurement does seem to inject genuine novelty into the world, the full picture is unresolved. But the block view sits at the center of modern physics, and it cannot be dismissed. And once you accept that the future already exists, a stranger possibility follows. The future might be reaching back. Cause comes before effect. This is one of the deepest beliefs we hold. The match is struck before the flame. The trigger is pulled before the bullet flies. The past determines the present, not the other way around. A small but serious group of physicists believes this is wrong. They argue that some quantum events may be partly caused by what happens later. The future, in their view, can reach backward and influence the past. This is called retrocausality, and it is one of the most controversial ideas in modern physics. The motivation comes from quantum mechanics, the strangeness we have already explored, the wave function collapse, the entanglement, the delayed choice experiments, all point to something odd about the relationship between time and measurement. These standard interpretations require either non-local influences spreading instantly across space, or the abandonment of definite properties before measurement, or branching parallel worlds. A small number of physicists prefer a different solution. They allow influences to travel backward in time. If a future measurement can affect a past quantum state, the strange correlations of entanglement can be explained without breaking locality. The information does not jump across space. It travels through time, forward in some cases, backward in others. This view goes back to the early days of quantum theory. The American physicist John Wheeler and his student Richard Feynman developed a version of electromagnetism in the 1940s, in which signals could travel both forward and backward in time. The math was elegant. It made successful predictions, but its retrocausal implications were too uncomfortable for most physicists, and the idea was largely set aside. It has been revived in the past 2 decades. The Australian physicist Hugh Price and others have argued that retrocausality may be the cleanest way to make sense of quantum mechanics. Some recent experiments have been designed specifically to test retrocausal models. The results, while not conclusive, have been intriguing. Several variations of the delayed choice experiment have produced data that fits naturally with a backward in time interpretation. There is an important caveat. Retrocausality, as physicists describe it, does not allow the kind of time travel we see in fiction. You cannot send a message to your past self. You cannot warn yourself about a future event. The retrocausal effects are subtle. They show up only at the quantum level. They do not allow macroscopic information to flow backward, but they may underlie the deepest behavior of the universe. Every entangled pair in this view is a system whose past and future are jointly determined by both endpoints. The particle does not just carry information forward, it also receives information from where it ends up. If retrocausality is real, the block universe makes more sense. In a static four-dimensional structure, with all moments equally real, there is no fundamental reason information should only travel from earlier coordinates to later ones. The arrow of time, as we have seen, is a statistical effect, not a fundamental law. At the deepest level, the universe may not respect the direction we feel so strongly. This raises strange possibilities about consciousness. If our brains are physical systems, and physical systems can in principle exhibit retrocausal effects, then the connection between mind and time may be more complex than we assume. Some researchers have speculated, controversially, that conscious experience itself involves a small retrocausal element. The evidence is weak. The idea is provocative. The boundary between ordinary causality and quantum strangeness is still being mapped. Most physicists remain skeptical of strong retrocausality, but the door has not closed, and the question of consciousness, hovering at the edge of these debates, has its own deep puzzle. Some thinkers have proposed that consciousness is the missing piece of the entire puzzle of physics. That awareness itself may be what collapses the wave function. Roger Penrose is one of the most decorated theoretical physicists alive. He shared the Nobel Prize in Physics in 2020 for his work on black holes. He helped lay the foundations of modern general relativity. He is not a mystic. He is not a fringe thinker. And he believes that consciousness itself is connected to the collapse of the quantum wave function. His proposal, developed since the 1990s with the anesthesiologist Stuart Hameroff, is called orchestrated objective reduction. It is a serious, if heavily debated, attempt to solve two of the deepest problems in science at once. The measurement problem in quantum mechanics, and the hard problem of consciousness. The hard problem asks why there is any subjective experience at all, why the firing of neurons gives rise to the inner feeling of being someone. We can describe the brain in terms of chemistry, electricity, and computation, but those descriptions never quite explain why these processes are accompanied by awareness. There is something it is like to be conscious, and no scientific account has fully captured why. Penrose argues that consciousness is not pure computation. It involves something non-algorithmic, some process that classical brains, viewed as wet computers, cannot perform. He believes the missing element is quantum. Specifically, he believes that the brain hosts large-scale quantum coherence, and that the collapse of these quantum states is what produces moments of conscious experience. The collapse, in his view, is not the standard sort. It is gravitationally driven. He proposed that once a quantum system becomes massive enough to bend space-time in measurable ways, it must collapse on its own, even without measurement. This is sometimes called gravitational decoherence. It is a real physical proposal, and experiments are now testing whether such gravity-driven collapse exists. If it does, and if the brain can exploit it, then consciousness becomes a series of these tiny collapses. Each moment of awareness is a brief unification of countless quantum states, snapping to a single classical reality. The brain rides the stream of collapses, and we experience the sequence as the flow of thought. The idea is highly controversial. Most neuroscientists do not believe quantum effects can survive in the warm, wet, noisy environment of the brain. Quantum coherence is fragile. It requires extreme isolation and low temperatures. The brain is the opposite of those conditions. Penrose and Hameroff propose that the coherence happens inside microtubulars. These are tiny tube-shaped structures inside neurons, made of proteins. They argue that the geometry of microtubules might shield quantum states long enough for coherence to play a role. The biological community is largely skeptical. Some studies have offered support, others have offered serious challenges. The debate is ongoing. What makes the idea remarkable is not whether it is right. It is the fact that a Nobel laureate of Penrose's stature seriously proposes that the deepest puzzle of quantum mechanics and the deepest puzzle of consciousness might share a single solution. He is not arguing that the brain is a magic computer. He is arguing that the brain may be a place where the universe performs some of its most fundamental operations, and that subjective experience is what those operations feel like from the inside. The full theory may turn out to be wrong, but the question it raises does not go away. What is the relationship between awareness and the structure of physical law? Why does the collapse of the wave function feel like anything at all? Why is there something it is like to be a piece of the universe looking at itself? These questions point to an even deeper one. If observation matters this much, what makes a reality stable enough to share? How does a single, common world emerge from countless private quantum events? The answer may lie in something called quantum Darwinism, and it may explain why we all see the same world, despite the wildness underneath. You see a tree, your friend sees the same tree, a camera nearby records the same tree. 3 different observers, 3 different sets of eyes and senses, agree perfectly on what is there. This sounds obvious. From the perspective of quantum mechanics, it should not be. If quantum systems exist as superpositions until they are observed, and if every measurement collapses the wave function, then why do different observers always end up agreeing on the same outcome? Why is there a single shared world rather than many different private ones? The standard answer used to be a vague reference to decoherence. Quantum systems interact with their environment. The strangeness gets washed out, and we end up with classical reality. This is true as far as it goes, but it does not fully explain how multiple observers consistently see the same things. The more refined answer is called quantum Darwinism, proposed by the Polish-American physicist Wojciech Zurek, beginning in the early 2000s. The idea is that classical reality emerges through a kind of selection process. Quantum information about a system gets copied many times into the surrounding environment. The system interacts with photons, air molecules, dust particles, fields, and every interaction imprints information about the system onto whatever it touches. Most of the quantum strangeness is fragile. It cannot survive these constant interactions. Only certain robust properties manage to imprint themselves consistently. Those properties get copied across many environmental witnesses. Different observers sampling different witnesses all read the same robust information. That is why we agree. Not because there is a single classical reality underneath, but because the only quantum information that survives the storm of interactions is the kind that gets broadcast to many places at once. It is a kind of evolutionary process. Properties compete to get imprinted. The fittest properties, the ones that copy themselves most reliably, win. They become the classical features we observe. The others vanish. Experiments have been conducted to test this. In 2019, a group of physicists, including Zurich himself, ran experiments in which a small quantum system interacted with the controlled environment of photons. They could measure how information about the system spread through the photons. The pattern matched the predictions of quantum Darwinism. Robust information was copied widely. Fragile information was not. This is one of the most promising frameworks for understanding why the world looks classical at our scale. It does not require a special role for human observers. It does not require collapse to be a real process. It explains the appearance of a shared world as a side effect of how quantum information propagates, but it has implications that are still being worked out. If reality is whatever survives the copying process, then the world we see is a thin shell of robust information riding on top of a vastly larger and stranger underlying structure. Most quantum information is hidden. Most of what exists, in the technical sense, is invisible to us. We see only the part that the environment broadcasts. This is humbling. The classical reality we treat as everything is only a curated highlight reel of the full quantum state of the universe. The rest is real but unreachable. It is washed out before we can detect it. Quantum Darwinism is still a developing theory. Not all physicists agree on its scope, but it offers a glimpse of why the universe at our scale feels so solid, so stable, so consistent across observers, even though the foundations are anything but. It opens onto an even stranger idea. If reality is information, and observers read what they can of it, then maybe the universe is not made of stuff at all. Maybe it is made of mathematics, and maybe we are inside the math. The physicist Max Tegmark of the Massachusetts Institute of Technology has spent years arguing for an idea so extreme that even his colleagues hesitate to discuss it. He believes the universe is not described by mathematics. He believes the universe is mathematics. This is the mathematical universe hypothesis, and it is one of the most radical proposals in modern physics. The idea comes from a long-standing puzzle. Why does mathematics describe the physical world so well? Galileo wrote that the book of nature is written in the language of mathematics. Eugene Wigner, a Nobel-winning physicist, called this the unreasonable effectiveness of mathematics. Pure mathematical structures, developed for their own sake by mathematicians who were not thinking about physics, turn out, again and again, to be exactly the structures the physical universe obeys. Why? Why should equations on paper match the behavior of stars and atoms? Tegmark's answer is brutal in its simplicity. Mathematics describes physics so well because physics is mathematics. The universe is a mathematical structure. Every property, every law, every event is a feature of this structure. We are patterns inside the math. The view has consequences. If the universe is a particular mathematical structure, why this structure and not a different one? Tegmark argues that all mathematically possible structures exist. There is no reason for nature to single out one set of equations over another. Every consistent mathematical structure is, in a real sense, a universe. The set of all such structures forms an ultimate multiverse. This is even more sweeping than the multiverse from inflation. It is even more sweeping than the many worlds of quantum mechanics. It says that every possible mathematical universe is real. The universe is governed by familiar physics. The universe is governed by unfamiliar physics. The universes that consist of nothing but a single equation. They all exist. Most of these universes are uninhabitable. Most have no observers. We naturally find ourselves in one of the rare ones complex enough to support self-aware substructures. This view is breathtaking and deeply controversial. Critics argue that it is unfalsifiable. There is no experiment that can distinguish a mathematical universe hypothesis world from any other. The proposal sits at the border between physics and philosophy. Some physicists view it as a useful framework for thinking about cosmology. Others view it as an overreach that mistakes a good language for an underlying reality. Tegmark has acknowledged the criticisms. He argues that the hypothesis, while currently untestable, is the cleanest explanation for several features of the universe. It explains why mathematics is so effective. It explains why the universe seems fine-tuned. It explains why so many possible worlds appear to be genuine descriptions of physical realities. There is something stranger about this view that often goes unmentioned. If you are a pattern inside a mathematical structure, then your existence does not depend on being computed or simulated. You simply exist as part of the structure. The structure does not need to be running anywhere. There is no machine. There is no time when it is being executed. Mathematical structures, like the number 5 or the Pythagorean theorem, do not need to be implemented to be true. They simply are. In Tegmark's view, the universe is the same. It does not need to be made of matter, or energy, or fields. It is a self-existing mathematical pattern. We are subroutines inside it. The substrate, if there is one, is the abstract realm of mathematical truth itself. This pushes physics into territory that brushes against pure metaphysics. Whether or not the hypothesis is correct, it forces a question we cannot easily set aside. If observers shape reality, and observers themselves are patterns inside a mathematical structure, then what happens when two observers disagree about what they see? The answer to that question may be the strangest result in all of modern physics. A physicist sits in a sealed lab and measures a quantum particle. The particle was in a superposition. After the measurement, it is in one definite state. The physicist sees the result. Now another physicist, outside the lab, who cannot see what happened, considers the entire lab as a quantum system. To this outside observer, the lab is in a superposition. The first physicist, the equipment, the particle, All of it together exists in a blurred quantum state, with no definite outcome until the outside physicist opens the door. Both descriptions are correct. According to the quantum mechanics, both observers are right. This is the Wigner's friend thought experiment, named after the physicist Eugene Wigner, who proposed it in the early 1960s. For decades, it was treated as a philosophical curiosity. Then, in 2019, it became real. A group of physicists at Heriot-Watt University in Edinburgh ran an experimental version. They used entangled photons to create a small system that played the role of an observer measuring another quantum system. They then made independent measurements of both layers. The results were stunning. Different observers, applying quantum mechanics correctly, ended up with logically incompatible accounts of what had occurred. Not different opinions, not different perspectives, different facts. The experiment was based on a theorem published by physicists Daniela Fraukiger and Renato Renner. They proved that under 3 reasonable assumptions, including that quantum mechanics applies to all systems, that observers can use quantum mechanics consistently, and that observed outcomes are objective, you reach a contradiction. One of the assumptions has to give. Most physicists agree that the assumption that gives is objectivity. There may be no single observer-independent fact about what happened in a quantum measurement. The world we share may not be as singular as we thought. Different observers may inhabit slightly different versions of reality, with no way to reconcile them into one master account. This is a quiet earthquake. For most of the history of science, we have assumed that there is one world. The observers may have different views of it, but the underlying facts are objective. The Wigner's friend experiments in their modern form suggests that this assumption may be wrong at the quantum level. If 2 observers can disagree about whether a measurement has happened, then the notion of a single, agreed-upon timeline of events starts to fray. The world begins to look perspectival, not in a soft, philosophical sense, in a hard, physical sense. Some physicists try to escape the conclusion by invoking many worlds. In that view, both observers are right because they are now in different branches. There is no contradiction because the apparent disagreement spans worlds. Other physicists embrace the result and argue that quantum theory simply does not support a single, observer-independent reality. They lean toward what is called cubism, or quantum Boxianism, in which probabilities and outcomes are observer-relative. Either way, the picture is shaken. Objectivity, the bedrock of science, may have to be carefully relaxed in light of quantum mechanics. The implication ripples outward. If reality is observer-relative at the deepest level, then the everyday agreement we experience between observers is itself a kind of negotiated effect, maintained by countless interactions, stabilized by quantum Darwinism, but not absolute. We share a world because the world makes sharing easy at our scale. Underneath, there is no master copy. This is uncomfortable. It is also the cleanest reading of the experiments, and it leads finally to the deepest question in physics. The question that physics may not be able to answer at all. The question of why anything exists in the first place. Physics has explored the inside of atoms. It has mapped the structure of galaxies. It has charted the behavior of black holes and traced the geometry of the early universe. It has done all of this with breathtaking precision. There is one question it cannot touch. Why is there something rather than nothing? This is the deepest question in metaphysics, and it spills into physics whether physicists like it or not. The universe exists. Space-time exists. The laws of physics exist. Why? The standard response from scientists is to point to physical theory. The universe arose from a state we do not fully understand, governed by laws that we are slowly uncovering. But this only pushes the question, why those laws? Why that initial state? Why anything at all rather than the simpler alternative of nothing? Some physicists have tried to answer. The American physicist Lawrence Krauss wrote a book in 2012 arguing that something can come from nothing through quantum mechanics. An empty space, he pointed out, is not truly empty. It has structure. It has fields. Pairs of virtual particles flicker into existence and annihilate themselves. From this, larger structures might emerge. This argument was widely criticized by philosophers. The nothing in question is not the philosophical nothing. It is a quantum vacuum, which is itself a complex structure governed by laws. It is something. The deeper question of why there is even a quantum vacuum, why there is a stage on which physics can play, remains untouched. The British physicist Stephen Hawking, working with James Hartley, proposed a no-boundary condition for the universe. It suggested that time itself emerges smoothly out of a kind of imaginary mathematical structure, with no need for an external cause. The universe, in their picture, does not have a beginning in the usual sense. It is a closed manifold with no boundary, and its existence is built into its own geometry. This is a real proposal, taken seriously by cosmologists, and it offers a partial response to the question. Even so, it does not fully address the original puzzle. Why is there no boundary geometry there? Why is there any geometry at all? Why does any structure exist that can be described by mathematics? Some thinkers have argued that the question itself is misformed. They suggest that nothingness, in any deep sense, may be impossible. That existence is the default state, not a special outcome that needs an explanation. The philosopher Derek Parfit explored this carefully. He argued that perhaps existence is simply what is, with no further reason needed. Others have argued that if every possible mathematical structure exists, in the sense of Tegmark's mathematical universe hypothesis, then the question dissolves. Existence is automatic. All possible patterns are real. The only question is which pattern we are. Still others push back. They argue that even the existence of mathematics, of possibility, of structure itself, demands an explanation. The question does not disappear by being relabeled. It only retreats further. There is no consensus answer. There may never be one. Physics, in its method, examines what exists and how it behaves. The question of why anything exists at all sits just outside its reach. Physicists who confront it usually do so as private musings, late in their careers, in essays rather than papers. But the question matters. It hovers behind every other puzzle we have explored. The fine-tuning, the arrow of time, the strange behavior of quantum measurement, the existence of consciousness. All of these are smaller versions of the same wound. Why are there laws to obey? Why are there observers to perceive them? Why are we here to ask? Physics gives us the most accurate descriptions of reality humans have ever developed. Yet it cannot tell us why reality is there to be described. The universe answers many questions. This one it keeps to itself. And one more puzzle still waits. A puzzle about whether everything we see has a hidden mirror. A second universe, twinned with our own, running in reverse. There is a deep symmetry in physics called CPT. It stands for charge, parity, and time. Charge means swapping every particle with its antiparticle. Parity means flipping the spatial coordinates, turning right into left. Time means reversing the direction of time itself. The combined operation CPT is one of the most fundamental symmetries we know. Every well-tested theory in physics respects it. If you take the universe, reverse all charges, mirror it spatially, and run it backward in time, the result obeys exactly the same laws. This is not an obvious fact. It is a deep theorem, derived from very general assumptions about how physics works. And it suggests something strange. The universe might have a partner. In 2018, 3 physicists at the Perimeter Institute, Latham Boyle, Kieran Finn, and Neil Turok, proposed a striking idea. They argued that the universe should be considered as one half of a mirror pair. On the other side, before the Big Bang in some sense, there is another universe. Identical in laws, but with charge, parity, and time flipped. From within either universe, the other looks like an antiverse running in reverse. The proposal was an attempt to solve several puzzles at once. The matter-antimatter asymmetry, why our universe contains so much more matter than antimatter, was unexplained in standard cosmology. The arrow of time, why entropy started low, was unexplained. Their model offered a clean answer. The pair of universes, taken together, are perfectly symmetric. Each universe, taken alone, has an arrow of time, an excess of matter, and other features that look anomalous. Across the pair, everything balances. The model also predicted specific properties of dark matter. They suggested it might be made of extremely heavy neutrinos, born sterile, produced in the early universe. Some experiments have looked for such particles. The results so far have been inconclusive. The model is alive. It is not confirmed. The mirror universe is a haunting picture. From here, we cannot reach it. There is no signal, no message, no possibility of contact. It is causally disconnected on the other side of the Big Bang, in a sense that makes ordinary travel meaningless. But if the model is right, it exists. It has its own galaxies, its own stars, its own history. It runs in time-reversed mirror image of ours. Whether it has observers like us, no one can say. The laws are mathematically symmetric. Complexity may emerge in the mirror universe, just as it did here. From its perspective, our universe is the antiverse. The sense of which side is real depends entirely on where you stand. This is one of several mirror universe proposals. Others come from different theoretical traditions. Some suggest that there might be a hidden sector of the standard model, made of mirror particles that interact only weakly with our world. These mirror particles could be candidates for dark matter, lurking in our own galaxy, ignoring our atoms. Searches for such particles continue. The deeper point is that symmetry in physics has consequences. Our universe respects CPT. It does not necessarily respect each individual letter. Charge symmetry is broken. Parity symmetry is broken. Time symmetry is broken. Only the full combined operation is preserved. Why are individual symmetries broken while the combination is exact? No one fully knows. The breaking patterns we observe, including the dominance of matter over antimatter, are part of the unsolved structure of the early universe. If the mirror model is correct, then every fact we have, every observation, every measurement, has a twin somewhere on the other side. A particle we call an electron is matched by a positron there. A galaxy here is matched by an anti-galaxy there. The universe is more symmetric than we thought, with the asymmetry showing up only because we live on one side of the symmetry. This is one of the cleaner ideas in modern physics, even if it remains speculative. It offers a kind of consolation. The strangeness of our universe may be balanced, somewhere we cannot see, by an equal and opposite strangeness running in the other direction. But it raises the final question. The one no theory has yet answered. What is the limit of what we can know? We have walked through a long catalogue of strangeness. Particles that exist in many places at once. Black holes that scramble information. Space-time that may be a hologram. Universes nested inside larger universes. Time that may not flow. Reality that may not be one. A pattern has emerged. Every layer of physics we open reveals deeper layers below. Every answer points to harder questions. The universe does not exhaust itself. It keeps unfolding. But there may be a limit. There are several reasons to suspect that some questions are permanently beyond our reach. The first is causality. Our observable universe is bounded by the distance light has been able to travel since the Big Bang. Beyond that horizon, things may exist, but we cannot ever see them, communicate with them, or test theories about them. Other bubble universes, if they exist, are walled off behind the horizon of cosmic expansion. We can speculate. We cannot verify. The second reason is energy. Some questions, like the structure of space-time at the Planck scale, may require energies so high that no possible experiment could ever reach them. We can write equations about strings vibrating in 11 dimensions. We cannot build a particle accelerator the size of the galaxy. The energies involved are simply not available. The third reason is more subtle. Some questions may not have answers at all in the form we expect. The question of why anything exists, the question of what consciousness is, the question of why the laws of physics are what they are, may be beyond the reach of physics in principle. They may require frameworks we have not invented. They may require frameworks no observer embedded inside the universe can develop. There is a phrase Werner Heisenberg used. He said that what we observe is not nature itself, but nature exposed to our method of questioning. The methods we use determine what we can find. Physics is a powerful method. It may not be the only one needed, and it may have boundaries we cannot easily see from inside. A real example of this is the black hole interior. According to the most careful current calculations, the interior of a black hole is encoded somehow in its surface. The geometry inside, in any traditional sense, may not be directly accessible. Information from inside leaks out through Hawking radiation, but only in subtle correlations that might be impossible to reconstruct in practice. We may know in principle that information is preserved. We may never be able to read what was there. Another example is the very early universe. Before the cosmic microwave background was emitted, the universe was an opaque plasma. We cannot see directly what happened. We can use particle physics to reason about it, but the further back we push, the more the conditions exceed anything we can recreate. The first instant of the Big Bang may be a permanent black box. This does not mean physics is failing. Physics has succeeded beyond any expectation. We have mapped the constituents of matter. We have measured the expansion of the universe. We have observed gravitational waves from black holes colliding billions of light years away. We have detected the ghostly hum of the cosmic background. We have built theories that predict the masses of particles to extraordinary precision. The triumphs are real, but we are inside the system we are studying. We are made of the same particles. We obey the same laws. We are limited in the energies we can produce, the distances we can probe, and the frameworks our minds can build. These limits are not signs of failure. They are signs of being what we are, conscious patterns, embedded in a universe that is bigger than our methods. What this means for the future is open. Maybe new methods will emerge that crack puzzles now thought permanent. Maybe new observations will overturn ideas that look solid today. Maybe the universe will keep yielding deeper secrets without limit. Or maybe we will run into a wall, and what lies beyond will remain forever beyond. The honest answer is that we do not know. The universe has surprised us so many times that confident predictions about what we cannot know often prove wrong. But equally, the universe has hinted again and again that there are layers beneath layers, and that no observer inside it may ever see the bottom. What we can say is this: the reality we walk through is far stranger than the surface suggests. The chair, the room, the body you live in, the hands you use, all of it is woven from quantum threads, possibly projected from a flat surface, possibly one branch of an infinite tree, possibly part of a mathematical structure that needs no substrate. You are in it. You are made of it. You are, in some sense, asking a question that the universe is asking through you. And the most stunning fact of all is that the universe lets us ask, that the laws it obeys are mathematical enough to be uncovered. That consciousness, however it arises, can hold a model of the cosmos inside a single skull. The deepest theories in physics make scientists question reality. They should. Reality has earned the questioning. It is not what it seems. It may not be what it can be made to seem either. The next century of physics will test ideas that make today's strangeness look tame. We are not at the end. We are barely past the beginning. The walls of reality have started to crack. What lies behind them is still arriving.